Imagine you want to turn an LED on. Before 1960, you would have to resort to a complicated process called soldering, which involved heating components up to extreme temperatures. But you don't have to, all because of the breadboard. Now, the breadboard is made up of a bunch of metal pins, and electricity can travel through these metal pins, but never into the next one. This applies for both rows and columns, as you can see here. Now, using it in a breadboard, you can make a bunch of cool things. But how does a breadboard truly work? Every atom has a nucleus, and inside of this nucleus are protons and neutrons. Now, around the nucleus are two rings. Now, these rings have different energy levels. More on that later. Anyways, orbiting these two rings are a bunch of electrons. And it's important to know that according to quantum mechanics, we may never know these electrons' position. They can really be anywhere, and we just know the probability of being in a certain position. But let's just simplify it for now. Well, this is an insulator, where the electrons are kept close to the nucleus. But in a conductor, if a specific amount of energy is provided, an electron can escape. Now, since electrons are negatively charged and protons are positively charged, this is a positively charged ion, since there are more protons than electrons. Now, if you added two electrons, this would become a negatively charged ion. Now, if you have a negatively charged and a positively charged ion together and energy is provided, an electron will automatically jump to the positive ion, and an electron will be taken from the negative ion, making them both neutral. Now, the pressure that forces this change to happen is voltage, and there doesn't need to be voltage in order for an electron to jump from the outer ring to the inner ring, since it's attracted to the nucleus. This actually creates energy. Now, if the inner ring is full, obviously, then an outer ring electron can't jump inside. But there needs to be energy in order for an electron from the inner ring to enter the outer ring. Now, we can visualize this atom as two lines, and we can put a bunch of these atoms together. Now, when two atoms are together, their outer rings make more of a cloud, and the inside and outside of those clouds become their own separate rings. The inner of these two rings is called the valence band, and the outer of these two is known as the conduction band. Now, we can account for this by adding two rings instead of just one, and removing the inner ring. Now, after all of this is done, we finally get ourselves an energy graph, where different energy levels are shown in different locations. Now, the conduction band is automatically empty, but if we give some power, an electron from the valence band can try to jump, but if not enough power is provided, it can't go through. Now, the amount of power that's required to bring it to the conduction band is known as the band gap. Now we can look at a real-life example. This is isolated silicon with 4 out of its 8 electrons filled in the valence band. And if we get multiple of these, it fills the whole valence band. Now, as previously mentioned, electrons can jump into the conduction band and conduct current through the material. Now, this doesn't do much, but we can switch one of these atoms over here of silicon into something like phosphorus, which carries an extra electron. Now, this electron has a higher energy level than the valence band, but a lower energy level than the conduction band. And this places it right beneath the conduction band, and it's full of electrons. Now, it's really easy for these to conduct current. Now, this is an N-type semiconductor because it comes with extra electrons. Now, the process of changing atoms in a group of atoms, like this, is called doping. Now, we could also do this with something like boron, which carries one less electron. And this creates an empty group right above the conduction band, which creates a P-type semiconductor. Now, if you combine P-type and N-type together, something interesting happens. So naturally they start moving, but some electrons will diffuse from N to P, and this creates an electric field. Now, as this electric field gets larger, it creates a depletion layer. But when electricity is given, it can get rid of this depletion layer. When an electron falls into the valence band of the P-type, it releases energy. But unlike atoms, this is scalable, and it comes out as light.